Okay, so this video picks up where the other one left off. We're still on this piece of paper, but we're on the back, and we are on the idea of reaction rates and how they relate to stoichiometry. Okay, so if you recall, the reaction rate, or the rate of a reaction, is the speed of a chemical reaction. Most of the time for us, they're going to be measured in units of molarity per second. It doesn't mean it couldn't be other units, but for us, that's what it's going to be. Okay, so molarity per second. Well, when we're talking about rate, we're talking about the change in the molarity over the change in the time. So if you think mathematically, and in chemistry, what symbol we've used for change, that symbol is delta. So delta means change. So the change in concentration over the change in time. And we're going to get very used to writing this. This is kind of symbolically a way to talk about the rate of something. And then again, that would lead us to units of molarity per second, because the change in concentration would be in molarity and the change in time would be in seconds. So this is the unit, but this is like the way we write it, and we're going to come back to that in just a second. Okay, so let's talk about some hypothetical reaction. And I'll just make it up, and we'll say, I'm not even going to use real things. So we'll say A making B. Okay, very simple. Reactant, product. All right, well, because obviously we're referencing stoichiometry in this, and stoichiometry has everything to do with mole ratio. So that's a 1, and this is a 1. So if that's my chemical reaction, then of 1 mole of this and 1 mole of this. Well, because my coefficients are equal, that means something kind of important to us. So I'm going to make this statement and then I'll explain. All right, I'll give you a second to get that copied. Okay, so because of my stoichiometry of this reaction and my 1-to-1, my 1 mole of A forming 1 mole of B, the rate, remember speed, the rate of the disappearance of A. Now, A is only disappearing because it's a reactant, and I start with it. So the only thing A can do is get smaller, and thus we're using the word disappearing. It's not really disappearing, it's just lessening. But the rate of disappearance of A is equal to the rate of the appearance of B. So think about a reaction. You have no product to start with. The only thing that can happen to your product is that it can get bigger. And so we talk about B appearing over time because of that. So because of that statement, we're going to try to write a little symbolic relationship like we just used a minute ago. And we're going to do it with the deltas. Okay, so let's talk about A. So if I want to do the rate, so what I'm essentially saying is the rate that A is disappearing is equal to the rate that B is appearing. But we know we can represent rate a little bit differently. So we said we can represent rate like this. The change in the concentration of A over the change in time is equal to the change in the concentration of B over the change in time, meaning their rates are equal. Now, the only thing we have to account for is that one's disappearing and one's appearing. And so the way we denote that is with a positive and a negative, kind of like the whole indo-exo, energy in, energy out thing. So we give disappearing the negative sign. So we would say that technically this is a negative because A is disappearing, and this is a positive. You don't have to write it, but I'm going to, because B is appearing. Again, for us, speeds aren't really negative. It's just that it's disappearing. It's just showing the direction that it's going. So this is kind of the relationship, and later you're going to have a packet that asks you to write the relationships like this. So that's the first one. We're going to do a couple more because this gets a little bit more complicated, but that's how you do this. Okay, that's how you relate the rates to each other based on stoichiometry. So this is a 1-to-1. Well, what happens when it's not 1-to-1, as we know is often the case? So let's do a different one. And I'll actually give you a real reaction this time. All right, let's say this is the reaction. Okay, so 2HI going to H2 and I2. Okay, so because this, in this case, our coefficients are not all the same. This one's a 2, and this is a 1, and this is a 1. So my mole ratios are different. It's a 2 to 1 to 1 relationship. So in this case, my rates are not going to be equal because this guy is twice as big. He's disappearing twice as fast as these guys are appearing. So this is how simple it is. And I'm going to show you first the easy way, which is how you're all going to do it. I'm positive because it's so simple. And then I'll show you the harder way that like a textbook would teach you, or probably a college professor. Okay, so I'm just going to make it up. Let's say that, how do I want to do this? The rate of H2 appearing is, I'm just going to make up some number, 1.6 molarity per second. Okay, so what I'm saying is H2 is appearing at a rate of 1.6 molarity per 1 second. And I want to know how fast this guy is disappearing. Well, watch how simple it is. It's all based on the coefficients. And you can do a sequence, just like we used to do for moles. Only this time we're going to do it for rates. So if this is a 1.6, well, what's this one going to be? Well, it's a 1-to-1. So it's also going to be a 1.6. So meaning these two are appearing at exactly the same rate. Well, what's this one going to be? This is a 1 and it's a 1.6. So this is a 2. So this has to be double. So 1.6 doubled. That better be 3.2 molarity per second. So again, your coefficients dictate your rates. Okay, so if you were asked to kind of explain the relationship here, well, you could say that H2 and I2 are appearing at the same rate because this is the same coefficient. But HI is, notice it's disappearing because it's a reactant. It's disappearing at a rate that's twice as big because this is a 2 in comparison to this and this being 1s. So it's that simple. Now, let's, I'm going to show you the harder way. Okay, so we're going to attempt to write out the, kind of the general expression for this. So let's talk about HI. So it's disappearing. And it's the change in the concentration of HI over the change in time. It's disappearing, so I better put a negative out here. And then this guy is the change in H2's concentration over time. Oh, sorry. And this guy is the change in I2's concentration over the change in time. These guys are all appearing, so I'm going to make them positive. Now, the issue here is we're trying to equate them. We're trying to make these equal statements. Okay? And so the way we do this, and this almost seems backwards until I show you that it's not, and I promise, so just hold out on me, is to make these equivalent statements, we have to account for the fact that this coefficient is not a 1, it's a 2. And so what you do is you put, you turn the coefficient into a, okay, let me see how to explain this. The coefficient is a 2, and so what you do is you move the 2 to the denominator of this fraction. So this becomes like a 1 over 2. Now, I know it seems backwards because over here we told you that the 2 was twice as big, and now it looks like this is half as much as these, and I understand. But that's the way you would write it. But now I'm going to show you that it is in fact totally true. Okay, so you ready? I'll prove it to you. And I promise you're never going to want to solve one like this, but it's worth seeing because your college professor might do it. All right, so let's go back to my original thing. I had told you that this guy's rate was 1.6. and I wanted to know this guy's. Now, I already know this is the answer, but I'm going to show you that I can get it in a different way using this. So, I don't care about this guy, right? We're not even discussing him, so forget him for a moment, and I'm looking at this relationship right here. Well, I just told you that the rate, this whole thing, that entire thing was 1.6 molarity per second. Remember, that's the number that I made up, okay? And so what we're saying is that this whole thing, this 1.6 molarity per second, is equal to, what I'm going to do for simplicity's sake is call this X, because that's what I'm trying to find. The change in concentration over the change in time, which is in fact the rate, which is going to be this, but you just don't know that yet. So I'm going to call it X, and so this leads me to a 1 over 2 times X. Now I know there's a negative out in front. Again, that's just the, that's just showing that it's going to disappear. So then if you were going to solve this for X, watch. How would you solve this for X? If you're uncomfortable with fractions, well then change that. So this is, what, 0.5, negative 0.5x. So how would you solve this for X? Well, you would divide by negative 0.5, right? Divide by negative 0.5. Cancel, 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 cancel. Now you got X equals 1.6 divided by half. Well, that's actually the same as 1.6 times 2, which leads you to 3.2 molarity per second. Technically, I ignored my negative sign. It should be negative. This one's actually negative 2. But so what I'm showing you, now you might be a little bit lost, and that's okay, because what I'm trying to prove to you is that you can do this equivalency of rates in 2 ways. One, with this kind of super complicated, the way the textbook teaches you, a process that doesn't make a whole lot of sense to us. Or you can use our idea of creating ratios out of rates, just like we have done out of moles, and it will work every single time, I promise. So anytime they give you one part of a reaction and ask you, what's the rate of something else? All you gotta do is make a sequence with the number that they gave you, and that's your answer. You can do it this way, totally, but it's a mess. But as long as you solve it correctly, you'll get the same answer. Look, we did 3.2 and 3.2. But both ways will give you the same thing. It's just that one's so much easier. So remember, it all goes back to that there are more than, there's more than one way to solve the problem. Mangoes, right? Remember, it's all about mangoes. It's all about solving it in a different way. Okay, and that is the discussion of reaction rates and stoichiometry.